So in previous class, we will discuss about some few types of non-covalent interaction, and just like ion-ion interaction, ion-dipole, dipole-dipole, and hydrogen bonding, and also little bit about the pi interactions. And this pi interaction, it may be pi pi types, or it may be cation pi interaction, or it may be anion pi interactions. These are these are the things we'll discuss in the previous class. Anion pi interaction, and another will be cation pi interaction, and another will be pi pi interaction. So from today, we will start with the another types of interaction. This is called van der Waal interactions. Okay. So this is also a type of non-covalent interaction. It is a weak interaction, or this the creation of this interaction. It is just like a collective form. That means some few types of weak interaction they can contribute to form van der Waal interactions. So there is a particular amount of energy range for van der Waal interactions, but this van der Waal interactions arises due to few number of factors. That means this is just like a collectively weak interactions. So these few factors they can contribute different types of interactions, and these three interactions or three weak interactions they collectively one can tell it is just like a van der Waal interactions. Okay, so particularly van der Waal interactions that arises from the fluctuations in electron density between the near atoms and the molecules. And this fluctuation in electron density it will arises due to three types of interaction. One will be London dispersion force, another will be dipole-induced dipole interaction, another will be short range repulsion, or simply it is called as Pauli repulsion. So if I told you what is London dispersion force, how can you define London dispersion force? So this London dispersion force it will arise just due to the transit dipole inside the molecule, or this is called instantaneous dipole that will arise inside the atoms or the molecules due to different electron environment.
क्लास शुरू होगा, प्लीज क्लास शुरू होगा।
of the distance. That means if the distance in between the nucleus and the electron, distance in between the nucleus of one atom and the electron cloud of the another atom, it will be less, then definitely the interaction amount will be more. If the distance will be more, then definitely the interaction will be less. So here, particularly these factors that are important or for the van der Waals force. First thing is that if you are taking a lattice or solid lattice, it should be densely packed solids. That means densely packed solids means if the particles or atoms of the solids, these are closely packed, then definitely the distance in between them will be less. When the distance in between the particles it will be less, it can make more amount of van der Waals force of interactions. So these types of van der Waals force of interaction, it is significant only when you are taking the densely packed solids. Okay. And second thing is that larger surface area molecules, the molecules that provide larger surface area, in this case also van der Waals force of interaction will be more. And the third thing, I already told you, the aromatic systems is a part of pi-pi interactions. Just previous examples, just like in graphite or in benzene, the pi electron cloud of the one ring, it can make also interaction with the pi electron cloud of another ring. So these types of interactions also, they can contribute little bit for van der Waals force. Okay. So the van der Waals force of interaction, it can arises at any instant of time. At any instant of time means this nucleus can make an interaction with these atoms at this moment, or this nucleus it can make interaction with the another atom's electron at this position. That means there will be no specific position or direction in a particular direction. This positive charge they can interact. They can interact this negative charge of this atom. They can also interact the negative charge of other atom also. They can interact also the negative charge of another atom. So that will be there will be no definite, there will be no definite direction for these types of interaction. So that's why these are called the non-directional nature and non-specific. That means it cannot only specifically interact with a particular these types of atom, it can also interact with another atoms. Okay, so this force it will be significant in these types of conditions. Okay, so you need to remember these important points. Okay, and these are the another points also when these types of van der Waals force also exist. Same thing, especially where the interactions are weak or absent or host-ghost inclusion complexes. These types of interaction also exist, particularly in cyclodextrins compound and the crystal packing. That means if there will be good packing of crystal, then definitely it will provide maximum surface area. If the surface area will be more, van der Waals force of interaction will be more. And the fourth point is closed packed lattice. Already I told you, this is densely packed solids. It's the same thing. Okay. Okay. So another factors are also important for this van der Waals force of interaction. The first one is the minimization of void space. Void space means if the empty space in between the atoms or molecules in the inside the lattice it will be less, then definitely the particles intermolecular distance it will be less and the interaction will be more. Second thing is maximize van der Waals contacts. Van der Waals contacts means the atoms that are participating in these interactions, its surface area it will be more. If the surface area will be more, the amount of force of interaction it will be also more. Okay. And another factor is that lattice energy also. So with the increase in lattice energy, it will also enhances the van der Waals force. Okay, so different types of systems, host-guest systems, or different types of systems we can consider in which the van der Waals force they will make a great role in these types of compounds. So particularly the molecular crystal compounds, in these types of crystal compounds, particularly van der Waals force, it will be help in packing up the molecules inside the solids. So in some few cluster compounds, the organic molecules are just like packed in a nature with just like a cluster. So the organic molecules sometimes in a cluster they can pack by the help of the van der Waals force also. Some inclusion compounds also just like cyclodextrin. In these compounds also van der Waals force has a great role. Okay, or some micelles in surface chemistry, your micelles are lipid bilayers. In this biological layers also or components also hydrophobic. The van der Waals force also has a impact. And in host-ghost molecules, just like brown ether complexes, cyclodextrin complexes, in this case also van der Waals force has an impact. So all types of compounds, in all types of compounds, definitely the van der Waals force has an impact. No doubt in this all types of compounds, other non-covalent forces are exist, but along with the van der Waals force of interaction also exists inside these four types of complexes. So these are all about van der Waals force of interactions. Okay, fine. Next we will discuss about hydrophobic effects. So the another important factor is that hydrophobic. So hydrophobic means just like water heating agent, or philic means just like water loving agents. So particularly here, if I say hydrophobic effect, that refers to the tendency of the nonpolar molecules or groups that will aggregate in a aqueous solution in order to minimize their contact with water. That means in a solution, some groups of nonpolar molecules are present, and this solution is a aqueous solution. So aqueous solution means definitely this is polar in nature. That means in a solution we are taking a polar solvent, or we are taking some nonpolar molecules or groups. So to minimize the contact with water, because this is a nonpolar hydrophobic thing, and the solvent is a aqueous solution. That means the solvent is water. This is a polar group. So to minimize their contact with solvent or water, the nonpolar molecules inside this solution they will aggregate. They will aggregate to form a cluster or cage type of structure. It is not because of hydrophobic molecules. It is because water prefers to make hydrogen bond with itself. That means in water molecule in a water solvent, they will make a rigid hydrogen bond within themselves, not with the non-polar surface. So definitely, if you are some molecules, non-polar molecules in water, then water cannot interact with these types of non-polar molecules. So in between the water itself, they will form a rigid hydrogen bond within themselves. Yes or no? So water is highly structured solvent, and they will form throughout the structure the hydrogen bonds in between them. If you can add some polar solvent, then definitely they will impact to the hydrogen bonding tendency or efficiency. But when if you add non-polar solutes, they will just like aggregate inside the aqueous solutions. So water molecules is highly ordered. Highly ordered means throughout the water molecules continuously through a long range area that can form hydrogen bond within themselves. And this order decreases the entropy of the system. So when these types of ordering occurs, particularly the entropy of the system will decreases. That means if inside the space lattice the molecules are or particles are moving randomly, then I can say the entropy will be more. So when the entropy will be more, we can say the reaction will be more feasible. It will be more feasible. That means thermodynamically, del G equal to how much? It will be equal to del H minus T del S. T del S. Del G is Gibbs free energy, del S is enthalpy, T is temperature, del S is entropy. So if del G value will be negative, then it will be thermodynamically feasible or favorable. So for negative del G value, these two factors are important. One will be enthalpy, another will be entropy. So here we are particularly determining or discussing about this entropy factor. If this entropy value will be more positive, then this minus T del S value will be more negative. So if this more negative, del G will be also. So del S value will decrease definitely. The del G will be positive. If del G will be positive, it will be
Sir, pardon, sir. Screen is
thermodynamically
not visible. Pardon, sir. Hello? Can you hear me, sir?
unfavorable.
Hello, sir.
So to
Sir,
reduce
screen is
this
not
effect,
visible.
non-polar groups. So to reduce this change in entropy, so to maintain or uh, this decrease in entropy, some of the non-polar groups they tend to cluster together. When they cluster together, the surface minimization occurs in contact with water. That means if the number of particles will be more, I can say contact of surface area will be more. So as a result, water becomes less structured or more rigid. So very hello, is it visible now?
Yes, sir.
Okay. So hydrophobic in hydrophobic effect, if you particularly add the non-polar molecules inside this solvent or polar solvent or particularly in aqueous solution, what happens particularly? So in this case, the polar solvent or the aqueous solution, they will make a rigid structure within themselves, just like water molecule make hydrogen bond with themselves. So when they will form a rigid structure or they will form a stable structure. That means throughout the solution, the randomness will decreases. If the randomness will be decreases, I can say this del S value, it will also decreases. So if this del S value will decreases, the del G will be less negative or the del G will be more positive. So once del G will be positive, then I can say this will be thermodynamically unfavorable or it will be thermodynamically not feasible. Yes or no? So to maintain the thermodynamically feasible process, the nonpolar molecules inside the solution, they try to cluster together. When the nonpolar molecules inside the solution, they will make cluster or they will aggregate it to form a cluster type compound. Then the water's rigidity structure, it will distort it. So once the solvent or water's rigidity structure distorted, then again the entropy will increases. So when the entropy further increases or del S value will increases, I can say the del G will be now negative and it will be thermodynamically favorable. So the aggregation of nonpolar molecules or hydrophobic groups inside this solution occurs. So when they will aggregate, they will distort it or they will disturb the rigid structure of solvent or water. So when the rigid structure of solvent or I can say water, they will break, they will form more number of water particles. So when the number of water particles will increases, I can say the entropy will increases. So once the entropy will increases, the del S value will increases, the del G will be more negative. So when the del G will be more negative, it will be thermodynamically more favorable. Yes or no? You can see here these pictures also, hydrophobic pictures also. These red lines, these are the hydrophobic groups, and the blue point, these are the this cup-like blue structure. This will be a hydrophobic solvent. Okay, so the hydrophilic and hydrophobic, they will self-assembly. They'll make a structure just like that. Okay, but when you'll add a hydrophobic solute or a non-polar group to a polar solvent or water, they initially they will make a structure like that, and further they will assemble to form the structure like that. That means it will form just like a micelle type structure. That means the hydrophobic parts it will lie inside the ring, and the hydrophobic parts they will make the circle. Okay, so they will aggregate it to form a structure like that. That means the nonpolar molecules or the hydrophobic molecules they will aggregate it to form a structure like that. Okay, so when the nonpolar molecules they will aggregate it, the solvent molecules distance it will increases. That means they will little bit distorted. The solvent molecules are the blue buckets, just like blue cups. They will distorted. They will make a distance in between them. When they will distorted, little bit distorted, the disorderness in between this complex it will increases. When the disorderness increases, the entropy value will increases, and the del G value will be negative. When Gibbs energy value will be negative, thermodynamic process it will be more feasible. So this hydrophobic effects it will be two types particularly. One is enthalpic hydrophobic effect, another is entropic hydrophobic effect. So why it is two types particularly? So for the feasible process, to make a thermodynamics process feasible or to make Gibbs free energy negative, these two factors, enthalpy or entropy, these are very very important. That means if the del H value will be more negative, then the del G will be more negative, or otherwise I can say if the del S value will be more positive, the del G will be more negative. So these two factors that are important for thermodynamic feasibility or favorability of the process. Okay, that's why the hydrophobic effect it will be divided into two types. Two types. One is enthalpic hydrophobic effect. Another is entropic hydrophobic effect. So you can read out here. In enthalpic hydrophobic effect, a nonpolar gas displaces water from hydrophobic cavity, and this displaced water rejoins the bulk solvent and lowering the system's energy. Lowering the system energy means initially it will decrease the entropy of the system. Okay, this is the representation of enthalpy hydrophobic effect. And another effect is that entropic hydrophobic effect. You can see here entropic hydrophobic. So these types of hydrophobic effect that will exist in micelle formation also, in DNA base also, in most of the biological processes. These types of hydrophobic effect it will exist. Okay, so you can write these types of examples in DNA stocking or lipid bilayer. These types of hydrophobic effect exist in protein folding. Okay, or in some host guest complexes, just like cyclodextrin, molecular case, self assembly monolayer. In this type structure, also, this hydrophobic effect it can also exist. Okay, or these are the energy discussions. These are the energy discussions for this hydrophobic effect. Okay, I just told you the two components are very important for thermodynamic feasibility. One is del H enthalpy, another is entropy. So the displacement of poorly solvated water lowers the system energy. So when this energy, system's energy initially decreases, the, in this case, the enthalpy will make an impact. It will be more negative. Or when water becomes less order or distorted, the number of water particles it will increases. So in this case, del S will be more positive. So these two factors that will combinedly affect this gives free energy, and the thermodynamic process finally it will be more spontaneous. That means here the enthalpy value will be more negative and del S value will be more positive. Then the del G will be more negative and the overall process will be more spontaneous. So this is all about the non-covalent interactions. You can remember all these things. Okay, and these types of questions also very important. These types of question. Name any two supramolecular chemists who received Nobel Prize in chemistry. Okay, the answers are also described in below. Okay, formula and question answers. There are three scientists initially I told you. They'll combinedly get Nobel Prize. Okay, in 1987. Okay, but the John Mary Lien is told as the founder of the supramolecular chemist. He's one of the founder of the supramolecular chemistry. Okay, you need to remember this name. They'll always ask who predicted, who give the concept of supramolecular chemist, or who gives the concept of the chemistry beyond the molecules, or the chemistry of molecular assemblies. So you need to remember this name, John Marillion. And John Marillion, along with two other scientists, in 1987, he got the Nobel Prize. Okay. This four, give the tabular form already in your material. All types of pi interactions, energy value, range, all these things are already mentioned. And the sixth number question is very important and popular also. Why are hydrophobic effects are more prominent in aqueous solvents than in organic solvents? What can be the answer? Why hydrophobic effects are more prominent in aqueous solution than in organic solvents? So organic solvents means particularly the non-polar solvents, THF, toluene, just like that. So what is the difference in between aqueous solvents or the organic solvents? Particularly in aqueous solvents, there will be existence of hydrogen bonding. But in organic solvent, there will be absence of hydrogen bonding. That differs in between these two solvents. So the particularly the aqueous solvents are the polar solvents and the organic solvents are non-polar solvents. So in polar solvents, if you take particularly aqueous means you are taking the water, particularly water polar solvent. So if you are taking the water, definitely there will be existence of hydrogen bonding. But in organic solvent, these are non-polar, there will be no presence of hydrogen bonding. That's why the hydrophobic effects are more prominent in aqueous solution. Because in aqueous solution, the structure are initially more or in an orderly manner. After the coagulation or after the aggregation of non-polar solute particles, Then again, this water particles structure, it will distorted, again energy value will increases. But for organic solvent, the environment is similar. Before aggregation also, the interaction in between this non-polar solvent is similar just like after aggregation. But here in aqueous solvent, the environment is different before aggregation of the solute and after the aggregation of the solute. You can see here also the answers. 6. The answer of the question 6. Water as a solvent is considered to be fast. Water is a highly structured solvent due to its extensive hydrogen bonding network. And this structure is distributed when the nonpolar molecules introduced, forcing in water molecules to reorganize into the order or cage-like structure, or they will form an aggregated structure inside the molecule. Then the ordering decreases entropy, which is thermodynamically unfavorable initially before aggregation. But after aggregation, the water's rigid structure it will break and it can get converted to a ordered form. Okay. But in organic solvent, you can see here chloroform also, benzene also, hexane also. Okay. There is lack of strong hydrogen bonding network. So solvation of nonpolar molecule in such solvent don't require major restructuring. It don't require major restructuring means the solvent and environment before the interaction of the nonpolar molecule is similar, just like the solvent interaction after the interaction with the molecule. Okay, so there will be no significant entropy change occurs or in the organic solvents if you add any nonpolar solute. So you need to practice all these types of important questions. Okay, so these are also very important. So next we will discuss in guest post molecules, particularly in supramolecular chemistry. What type of post molecules are exist in a supramolecular chemistry? It can be sometimes crown ether, it can be kryptanoid, it can be cyclotextrin. So now we will discuss about the types of the host molecules that will exist inside the supramolecular molecule, supramolecular chemistry. Okay. So first you just remember the definition of the supramolecular chemistry. Okay. In previous class we will discuss about it. Then these three scientists they got Nobel Prize for supramolecular performance in supramolecular chemistry. Okay. So these are few structures in supramolecular chemistry. You can see here, these are the ion channels, this is active synthesis, this is a bacteria process, biological process. Okay. See, all types of structures, the supramolecular chemistry types compounds are present. Okay, so from this biological processes, they will trace or get got idea about supramolecular interactions. That means ion channel means just like in our skin. Okay, we can say in our skin there will be some little interaction of the ions. That means the ions inside our skin or blood cells they can also get outside of our skin, but they maintain in a particular concentration. That's why, or these ions they will make an interaction inside the water particles or the blood particles, that the ions it cannot go outside the skin easily. Okay, that means the potassium ions or sodium ions they already exist with an interaction inside the molecule inside our body, so it cannot easily go outside. Okay, so this is the basic classification of the supramoleculars chemistry. So one type of classification is the rotaxane, catenanes, and dendrites, fullerenes, CNT means carbon nanotubes. So that means these types of structure they particularly have a specific type of shapes. Okay, and if you consider another types of structure, or just like crown ether, polyamine, cyclodextrin, or calixarin. Okay, these types of structure, they don't have particular type of shape. So some crown ether complex, they have small size also, and some crown ether complex, they have also larger shape also. Okay, but they will follow a particular pattern. That's why you can identify this will be cyclodextrin, this will be crown ether, like that. And this is a molecular assembly form of numerous number of molecules, or these are called amphiphilic molecules, just like micelles or lipids. So these all types of supramolecular molecules, they will be classified into three types. This particularly these three types. So one by one we'll discuss. Okay. So before discussion, so particularly the fundamental idea in supramolecular chemistry will be, one will be definitely a host site and another will be a guest site. That means this will be just like a host guest interaction, or in biology in plus two you already studied about lock and key theory. That means there will be a lock, it will be a fixed position, and a key will come, then it will interact in the with the lock. So here also it will be similar, just like a host guest chemistry. Then now we will discuss about what are the particular properties or specific properties of host and particular specific properties of guest. Okay. So particularly for the host guest interaction, it will depends on particular two factors. One will be selectivity, another will be the interaction energy. That means the selectivity will be more. That means the host and guest, they should have just like similar types of ions, or they should have just like same specified charge. That's why they can interact with each other. Or I can say simply, the host binding site, it will be just like face inward, and it will be just like converge. And the guest, when it will come to interact with the host, definitely it will, its binding side, it will be just like a opposite direction. So you can just see here, I can say just like a structure, post structure, I can draw a post structure. Similarly, just like this is a post structure. That means I can say this is the active side, or this is the binding side. This is a post. And when a guest will come from far away, okay, and this part will be the binding side. That means here, if I say this empty space or active side, it will be inward direction. I can also say that this guest binding side, this will be a outward direction. So the host guest interaction when occurs, that specific binding site, they will be in a just like opposite position. Here the active site or binding site, it will be inward towards the molecule, or towards this surface, and the binding site also, or I can say this will be, if this will be a binding site, this will be a binding site. So this binding site of the guest molecule, it will be just like outward. So the inward one one direction it will be inward, and the another guest direction it will be outward direction. Okay. The third condition is that when they will form complex, the two or more molecules held together in a unique structural relationships. That means there must be, after interaction in binding site, there must be a specific type of van der Waals force, or any types of non-covalent force that can exist in between them, so that the host and guest, they can bind and they can stable its position, they can form a stable complex. Or I can say simply, the host and guest, it should be complementary to each other. Okay. So for the achieving or maintaining this complementary nature, there are several factors we need to remember. Steric complementary. That means the host should be just like a larger molecule, and the guest, it will be a very small molecule. Then there will be issue in the formation of host guest interactions. So this, it should be just like a steric complementary. That means one should not be more bulky, another should not be very small. Okay. And the second factor will be interaction or chemical complementary. That means there will be existence of chemical forces. That's why this is called chemical complementary. Another will be larger contact areas. So when the contact area or surface area increases, definitely the interaction amount will increase. And fourth one is the multiple interaction sites. Same thing. The surface will be more, then the interaction side will be more. Here you can see here a picture of host. This is circle, and these are the guests. They can also fit inside the host. But this host cavity size, it will be preferable for this particular types of guest, not the smaller guest, not for the larger guest, for the exact cavity size guest. So this will form a complex like that. Okay, so in body or in our biological system, we can consider just like antibody is the host and antigen is the guest also. I already told you for binding of host and go guest, the two things are important. One is interaction, another is the selection or selectivity. Okay, same thing already mentioned here. Multiple interactions, strong overall binding, like that. And sometimes this is called the molecular assembly or host guest complexes. They will form a dynamic molecular recognition. Dynamic molecular recognition means particularly the van der Waals force or the non-covalent force in between the host and guest, it will be very very weak. So sometimes in a space lattice, we can say a larger number of hosts are present, a larger number of guests are present. Sometimes one of the guests it can make a it can just break from the host side, and another guest molecule it can also interact with the host side. So this sometimes there's the supramolecular chemist or supramolecular in supramolecular chemistry they will form some dynamic molecular recognition compound, and also sometimes they will form static molecular recognition. That means the host guest after binding they will be just behave just like a fixed manner. They will be just like a static manner. Further, the host guest breaking doesn't occur. Okay. Here also another example of host. Here also guest it will form to form host guest complex. So in particular dynamic molecular recognition, host molecules contain particularly two binding sites, and so it requires two guest molecules. So these two guest molecules are not binded at the same time. So the one of the fast binding guest molecule it will binding to the one side, then another guest molecule it will be binding to the another binding side, but their binding side is very very fixed. So I can say here, you can see here there will be circular empty space, or I can say this will be a cavity, and this will be a triangular shape, triangle, white triangle. This is also a cavity. That means these cavities are or the empty spaces are the one of the binding sites. So in first case, these types of guest molecule, this can fit into this cavity. They will form a complex like that. Then in second step, these types of another triangle or triangle structure or another triangle structure guest, it will form. It will interact with this cavity, and they will form again host guest complex. And so these types of interaction particularly found in dynamics molecular recognitions. Okay. And next we will discuss about the lock and key theory. So in lock and key theory, just like this is a substrate and this will be an enzyme. In plus two biology or botany, just remember lock and key theory. One will be the key substrate part, another will be the lock. So here you can see A, B, C. That means it is three different binding sites. So these 3 points I can say that the active sites or the binding sites. So the binding sites of the enzyme, it will interact with substrate binding site, and then again it will form a ES complex. ES complex means enzyme substrate complex. Right. Am I audible? Screen visible होता तो screen visible हो जी
हाँ,
ना ଏବେ visible ହେଲା ତ
yes, sir.
okay. Then we'll discuss about the spherical recognition. Spherical recognition means the cation or any type of specific types of anion or any types of guest molecule, they're trapped inside a spherical structure. Inside a spherical structure. Sometimes some non-cyclic linear ring also. They'll sometimes some non-cyclic chain also. They'll form a little bit circular structure. It's not a complete circle, but they'll form a they'll create just like a spherical environment. And at one point, at this point, this O is not in contact with this oxygen, but they can form a spherical structure or spherical environment. They cannot form a complete cycle, but they can make a spherical environment like that. And inside the spherical environment, these ions or guest cations or anions, they can also trap. They can also form a structure like that. Okay. So another popular host molecule, crown ether complex. So these are the crown ether complexes, the below structures. These are this complex 15 crown 5, this one will be 18 crown 6, and this one will be 21 crown 7. 21 means the atomic centers are 21 positions, just like 1, 2, 3, 4, 5, 6, just like throughout the circle. How many positions are present? 21 positions. So out of this 21 position, how many oxygen atoms are present? 7 oxygen atoms. So that's why the naming will be 21 crown 7. So this particularly these crown ether complexes, some specific crown ether, they can particularly fit into some specific types of cations. So if I say 15 crown 5, then specifically they can specifically fit the sodium plus ion. If you take 18 crown 6, that means here the cavity size it will increases. If the cavity size will increases, it can also trap a little bit larger cation. And here this cation is potassium ion. So potassium ion it will fit for 18 crown 6 complex. If you take 21 crown 7, then here the cesium plus ion, Cs plus. This is a larger cation, they can fit into the 12 crown 7 complex. Because here the cavity size will increases, so inside this structure, there will be specific types of cation they can fit into it. Okay. So this for the specific crown ether, specific patterns are necessary. So I need to remember all these things. Like, these all examples are very, very important. Okay. So if you want to discuss about crown ether, there are the crown ether complexes. We'll discuss about crown ether. So particularly crown ethers are first the artificial host molecules that are discovered, and this will be found as a byproduct of the organic reaction. So you can see here for the synthesis of bisphenol, this will be one bisphenol from impurities led to production of a small amount of cyclic hexide. Here also you can see from this reactant, with this reactant they will form this is basic product. But along with this basic product, sometimes they will again form also these types of byproducts. These types of byproducts, the scientists name them just like a crown ether complex. That means after the formation of this product, again this reactant group, they can also attack on this side and they can form these byproducts. So these byproducts are called crown ether complexes. So the discovery of crown ether complex that will arises from these organic reactions, and particularly from the byproduct, they'll get these types of compound and they will name these types of compound just like a crown ether complex. So why the naming is crown ether? Because the structure will be just like that. There will be just like it seems just like a crown, because the cyclic host or this host molecule it will just appears just like a crown on the head of the king. So that's why they will name just like as crown ether complex. So the crown ethers are named as follows, just like the number before the crown indicates the total number of atoms in the cycle. So here, if you named it just like as a 15 crown, just like a 12 crown oxygens. So that means 12 atoms are present, particularly carbon, oxygen, carbon, oxygen. So 12 center atoms are present. So is it predicting that crown ether is named as follows, just like the name before the crown ether, name before the crown ether. Class also করছি just like so this number, first this number, it represents how many atoms that will present in these centers, particularly these types of reaction centers, carbon, oxygen, carbon, carbon, oxygen, 12. And the number after, written after the crown word, this represents the number of oxygen atoms. 1, 2, 3, 4. So the number after the crown gives the number of oxygen atoms in the cyclic structures. So the oxygen atom, which is high electronegativity, can act as a binding site for the metal ion. Particularly, the cation that will be trapped inside the cycle, this will be stabilized by the oxygen atoms. That means oxygen lone pair, they can make interaction with this cation and they will stabilize this cation inside its cavity. The oxygen atom, which has a high electronegativity, can act as a binding site for metal ion or ammonium ions. Ammonium ions means you can take NH4 plus also inside the cavity through dipole ion interaction. Dipole ion interaction means the oxygen and this crown complex. It will act just like a dipole, and K plus it will be just like a ion. And the oxygen side it will be get partially negative, and the carbon will be partially positive. So here the negative part it will interact with the plus ion, K plus ion, Na plus ions. Okay, that's why these types of interaction are also sometimes called inside the ring. They will make dipole and ion interactions. So here ion will be the cation, and the dipole will be the crown complex. Okay, so you can see here 12 crown 4 complex. This is called 15 crown 5. This is 18 crown 6, and this is 12 crown 7. So here the inner diameter is giving the experimental inner diameter. Here the inner diameter value is 0.122 to 0.15. Here the inner diameter value is 0.15 to 0.22. Here the inner diameter value is 0.26 to 0.32. So gradually with increase in the diameter value or inner diameter size, it will increases. So if the inner diameter size will increases, that means it can easily trap the larger cations. Okay, so initially the 12 crown 4 it will be favorable for lithium ion, and the 15 crown 5 it will be favorable for sodium ion, and 18 crown 6 it is favorable for potassium ion, and this 21 crown 7 it will be favorable for calcium ion. Okay, sorry, this is not calcium, this is cesium. Last one is cesium. So they can ask short questions also. Uh, so you need to remember the exact crown size for exact cation. This is most important. You cannot say randomly, I'm taking a 12 crown 7 complex and K plus ion, they can fit inside it. Okay. So for specific crown complex, specific cation size, cation can fit inside it. So you need to remember the exact cation for exact crown ether complex. Okay, so further crown ethers they can be classified into different types according to its structure. One is called podants, non-cyclic hosts that are known as podants. Podants means these types of structure, non-cyclic structures. Uh, that I'll show you before 2 to 5 minutes before these types of structure, non-cyclic structure. They will form a spherical movement, but they will not form a complete cycle. These are called podant. So podant is also one type of crown ether complex. And another is the another monocyclic host molecules. that can include that are called as coronants, and the oligocyclic boards are also called cryptanoids. Okay, so these are the cryptanoid structures. These are the codon structures. So codon structure is not complete cycle. At one point, the atoms are not in connection with each other. That means in between them there will be empty space. Okay, so this can be one type of crown ether. This particular type of crown ether is called cryptanoid. So the simple coronants means particularly the 12 crown, 15 crown. These are the coronants. Okay, and these are the codons, and these are called cryptons. When there will be bicyclic structure, that means inside a cycle, another interaction exists like that. These are called cryptons. So another types of host molecule is also called macrocyclic polyamines, or these are called nitrogen-based cyclic hosts. That means here in position of oxygen, just like in crown ether, in position of oxygen, the nitrogen and hydrogen atom is present. So sometimes these are called also ether type of crown ether complex. Or these types of complex also, oxygen along with nitrogen, hydrogen, these types of structure also called thiac crowns. This is called that means in this cyclic structure, in some position of oxygen, you are placing nitrogen, hydrogen atom, then these are called the thiac crowns. If all the position of oxygen you are putting just nitrogen, hydrogen, then these are called thioether type crown. Then another important structure is cyclodextrin. So particularly the cyclodextrin that will exist in between the sugar structure in biological process, it can exist in between the glucose and sucrose just like that. So this glucose structure, they can form a polysaccharide bond in between them by making 1,4 linkage. So this linkage is called 1,4 linkage, or this linkage is called 1,4 linkage. So one of the glucose molecule, they can make interaction with another glucose molecule by in the 1,4 linkage. If the glucose molecules throughout the structure, if they will form a cyclic form like that, then I can say this overall structure just like a cyclodextrin, just like a cyclodextrin. If the alpha side of the glucose, it will make interaction with another glucose molecule, I can say alpha cyclodextrin. So if the beta side of the glucose molecule, it can make interact with another glucose molecule, and I can say beta cyclodextrin, just like that, gamma cyclodextrin, like that. Okay. So the glucose molecules, they can make polysaccharide bonds in between them through 1,4 linkage, and they can also form a cyclic structure like that. So this is glucose or the polysaccharide bond structure like that. This is called cyclodextrin. So it will form a macrocyclic ring like that, or it will form a host complex like that. Okay. So particularly the some other. Am I audible?
Sir. Yes, sir.
Okay. So these are some few important cyclodextrin structures. Here you can see also the cyclodextrin structures, just like they will form a cyclic ring, but some of the OH group it will be remain of the upward side of the cavity, and some of the OH group it will remain on the downside of the cavity. So this OH groups that will remain on the upper side, I can say just like a primary OH side, and the OH side that will remain towards the downward direction, I can name it just like a secondary OH side. Yes or no? And the cavity size, it will be just like a fixed cavity size. So alpha cyclodextrins, it will form a cavity size of 0.45 nanometer, and beta cyclodextrin, it will form a cavity size of 0.70 nanometer, and gamma cyclodextrin, it will form a 0.85 nanometers cavity size. Okay, so this is all about cyclodextrin and crown ether complex. Okay, so this is also one type of cyclodextrin complex. This cavity, it will be just like a host, and the naphthalene molecule here it will behave just like a guest molecule. It can come, or the two of the naphthalene it can come, or it can get trapped inside this cyclodextrin ring. So here the naphthalene it will behave just like a guest, and ring, this ring structure, this will be cyclodextrin. It will form by the summation of so many glucose through polysaccharide links. Okay. So in next class we'll discuss about other things, supramolecular devices or supramolecular catalysis, or some other few other types of host complexes. But this one, two, cyclodextrin and crown ether, this is very important, and most of the exam questions they will definitely ask from this part. Okay, so here also some few examples of host and guest. Okay, so if you add these types of host or receptor and these types of guest, then definitely this guest it will choose this particular specific site for this specific site for this interaction, and this guest it will go to towards this site for this interaction, and it will form a complex like that. That means for a particular type of guest molecule, the binding site is fixed, and the guest it will choose the binding site in host when it will fit properly. Okay. Here also some examples of hydrophobic effects. Here you can see these water molecules. This will be trapped inside this host structure, and here we are adding a solvated guest. So when the guest will go towards the cavity side of the host, the water molecule it will come outside this cavity. When the water molecule will come outside the cavity, this will distorted. This will be just like in a single form, monomeric form. So when these water molecules they will break into individual ions, atom molecules outside the ring, and I can say in the complex part or outside the ring, the entropy will increases. So once the entropy will increases, it will be thermodynamically more favorable. Okay. So here also anatomy of cyclodextrin, and this part will be the hydrophobic cavity. Here this part will be the cavity part for the part or site for interaction with the guest molecules, and this ring part will be the host molecule, and then the lower part will be the primary hydroxyl group, and another part will be the it will form a secondary hydroxyl group. Okay, so if you take alpha cyclodextrin, you can see the cavity size or diameter of the cavity will be 5.70 Armstrong. If you take beta cyclodextrin, the cavity size will be increases along with the host size. And if you take the gamma CD, you can see the guest cavity size also increases along with the host molecules length also increases. So this is the structure of anatomy of cyclodextrin. If they will ask a long question on cyclodextrin, we need to draw all these types of structures, and the structures are very easy. You just need to remember a little bit about its diameter value or a host complex length. Okay. So if you have any question, you can ask. এই কোশ্চিন সব প্র্যাকটিস করিব তোমার যে ম্যাটেরিয়াল ଦେଇଛି কোশ্চিন ଏକ ভেরি ভেরি ইম্পর্টান্ট ହେଲା जो क्वेश्चन आंसर ଦେଇନି ବି ତମେ जस्ट ମ୍ୟାଟେରିଆଲ ସର୍ଚ୍ଚ କରିବ ପାଇଯିବ କିଛି ଅସୁବିଧା ନାହିଁ ନହେଲେ ଗୁଗଲରେ ସର୍ଚ୍ଚ କରିପାରିବ ହେଲା
Sir, did the material
ओके टेल
this material is not able to we can
फॉर एग्जाम
no sir. The material we
or
cannot able.
material okay material you can get the igno material from your e Gyanakosh site ହେଲା if you want other types of powerpoint or other materials one of your from your class group they can send me a message I will send you one of you and you can distribute it among all okay
Yes, sir. Thank you.
so these types of particularly this MSc materials you can get from EPG Parsala. There will be a site also, government site EPG Parsala also, or from E Gyanakos also, or these types of materials also. These are self-made materials. Particularly these types of materials. These are class materials. You can collect from me also. Okay. These are the PowerPoint materials. And in previous class, I already show you the handwritten materials also. Okay. Handwritten materials are also available. You can collect it. So in supramolecular, the types of host molecule. This is the preliminary types of host molecule, both important. ଏଇଟା ବି ଯୋଉ ରହୁଛି ଏଇ ପାର୍ଟଟା the types of interactions. First question ଯୋଉଟା ରହୁଛି the type of interaction. They may ask long questions. What types of non-covalent interactions? ତ particularly ସେ ପଚାରି ପାରିବ ଯେ ଗୋଟେ ଦିଟା ଟାଇପର interaction ଦେଇପାରିବ ମତେ ହାଇଡ୍ରୋଜେନ ବଣ୍ଡିଂ ଆଉ ଭାଣ୍ଡରୱାଲ ଫୋର୍ସ ବିଷୟରେ ଡିସ୍କସନ କର ସବୁ ଡିସ୍କସନ କରିବ କିଛି ଅସୁବିଧା ନାହିଁ and you need to remember all these energy values not exact values but you need to remember and you can see here out of all these values the van der Waals force interactions value energy strength it will be very very less and out of the all non-covalent interactions the ion interactions strength it will be very large and this value is nearly equal to the value of a covalent bond strength okay so the strength you need to remember also. So thank you. If you have any question, I'm available on the meeting. Now you can ask. I'll just wait for further few minutes more.